Hello everyone, I'm Shengying from Shanghai Jiao University. I'm very grateful to the conference committee for attending this invitation to me. It is my great pleasure to be here today and talk about multi-omics analysis identifies rare variation in leptin PPR gene sets and hypermethylation of ABCG1 contribute to antipsychotics-induced metabolic syndromes. This study primarily focuses on schizophrenia, a severe psychiatric disorder. Individuals with schizophrenia often undergo different experiences. Typically, we categorize these experiences into two groups, positive symptoms and negative symptoms. In China, schizophrenia is a significant concern, affecting about 1 in 100 individuals throughout their lifetime. With China's vast population, this translates to over 6.4 million individuals, and yet almost half of these people don't receive the treatment they need. We have come a long way in treating schizophrenia. Imagine this, back in the day, our treatment options are pretty limited. Then the 1950s brought us the first generation antipsychotics, a significant breakthrough. By the 1990s, drugs like olanzapine, risperidone, etc., the second generation antipsychotics came onto the screen, and they are now the go-to medications for treating schizophrenia. Yet even with these advancements, treatment isn't always straightforward. About 30% of patients don't respond well to these treatments. Half of the patients experience weight gain. 10% even suffer from EPS, and roughly 20% developed late onset movement disorders. This study mainly focused on a specific issue, metabolic syndrome. This syndrome is a nasty combination of symptoms like central obesity, high blood pressure, wacky cholesterol levels, and messed up sugar levels. The incidence of metabolic syndrome in individuals with schizophrenia is alarmingly high, and it significantly raises the risk of cardiovascular disease and even death. The mortality rate among those with metabolic syndrome is much higher compared to the general population. The risk of metabolic syndrome in schizophrenia patients is over double that of the general population. A study published in 2020 shed light on the elevated risks associated with various antipsychotic drugs. In this study, the drugs with high risk are marked in red, signifying their potential for more severe side effects. It's noteworthy that some of the commonly prescribed medications, like the one marked by the orange dots, carry a substantial risk. The diagram illustrates the key experimental processes we have undertaken. We have performed genome-wide association analysis, exon sequencing, and genome methylation association analysis to identify the genetic and epigenetic biomarkers. Additionally, we have integrated all our multi-omics data to get a clear picture. Some genes caught our attention from initial analysis. To explore their potential, we tested them in C. elegans using high-throughput RNA screen, and any promising results we found in this warm screen were validated using cell line models and in mice. To kick off this project, we started with a rigorous process of collecting samples and recruiting participants. we made sure to exclude individuals who didn't meet certain criteria. Finally, 939 schizophrenia patients with or without match are remained for omics analysis. Here are the demographic baseline of the subjects. We conducted quality control and filtering of both genetic marks and samples, excluding some low-quality marks. Subsequently, we performed a genome-wide association analysis and adjusted for population stratification. Here is a hunting plot illustrating our research findings. Then we identified prominent signals in the region of chromosome 16. This is one of our key findings, and the plot displays the top several SNPs with significant associations. In the zoom-in plot, you can see that the region around this SNP exhibits a strong linkage pattern. Furthermore, there are several relevant genes adjacent to this region, including POLR3K and SNRNP25, etc. In our analysis of the whole exome sequencing results, we primarily focus on rare variants. We began with gene-based association analysis. To ensure the reliability of our data, we applied filters. First, we filtered out harmful mutations. Then we set a threshold with a minor allele frequency of less than 0.05. Additionally, we required that each gene had at least 2 or more mutations. After applying these filters, we performed analysis using methods such as CMC and Skittles. Our findings revealed that certain genes indeed exhibited a significant difference between the case and control groups. Subsequently, we conducted a pathway-based association analysis and found that both the leptin and PPAR pathways remained highly significant even after multiple corrections for p-values. We then performed sequencing on clinical samples to examine the gene expression patterns in these pathways. We observed notable difference in the expression of genes in leptin and serotonin pathways, further highlighting their significance in our study. Next, we conducted an association analysis for whole genome methylation. We began with analysis of differentially methylated sites, and this is the Manhattan plot depicting our findings. We identified 17 significant sites after FDR correction. Following this, we performed an enrichment analysis on these sites. Our analysis revealed an enrichment of genes related to mitochondrial ATP synthesis and the postsynaptic membrane pathway. Subsequently, we conducted an enrichment analysis among the top 100 differentially methylated positions, DMPs. We observed that these DMPs were more likely to be located in CPGR links and less likely to be in open C regions compared to the background distribution. Furthermore, the top 100 DMPs showed enrichment in promoter regions and transcription factor binding sites. In our analysis, we employed two software COMP and DMR kit to identify differentially methylated regions. Our results revealed the presence of 2 DMRs located in ABCG1 genes. And here is the details of the DMRs in ABCG1 genes. We conducted the DMR validation using CRISPR-based methylation modification in epigenetic cells. Specifically, we compared the lipid droplet formation after hypermethylation and hypermethylation of the DMR1 and DMR2 region in HepG2 cells. Additionally, we measured the Tg and Tc contents in HepG2 cells that had undergone CRISPR-based methylation modification 24 hours after treatment with olanzapine or a vehicle control. These experiments allowed us to assess the impact of methylation changes in these DMRs on lipid metabolism in HepG2 cells. We conducted a joint analysis of GWAS and methylation data. Our findings suggest that the differential methylation might be influenced by genetic variation. Specifically, we identified 1,662 cis MEKTLs and an FDR threshold of 0.05. Moreover, we observed that the effect size indicating the demethylation change per allele of this cis MEKTL were associated with the distance between the differentially methylated position and the MEKTL SNPs. We used the olanzapine-induced intestinal fat deposition model in C. elegans for more in-depth validation. Interestingly, during alpha stage, which aligned with early adulthood, we saw significant fat buildup in just 4 days of treatment. And this fat buildup persisted regardless of the bacterial strains we fed the worms. To dig deeper, we look at various datasets, especially focusing on genes from PPAR and leptin pathways, as well as those connected with GWAS and MEQTLs. After thorough analysis, we identified a total of 242 candidate genes within conducted high-throughput RNA screen in the worm model. In the end, we found 16 human homologous genes that appeared to be related to fat accumulation in the nematode model. These findings offer valuable insights into the genetic factors involved in lipid accumulation. And we quantified the expression of candidate genes in both the vehicle and the olanzapine treatment groups. Out of the initial candidate genes, 11 genes remained significant and showed a differential expression between the two groups. These genes appear to be particularly relevant to the effects of olanzapine treatment. In a independent cohort, we conducted an identification process to identify candidate genes. Interestingly, most of the 11 candidate genes that are previously identified showed significantly higher expression levels in the match group. This suggests a strong association between these candidate genes and metabolic syndromes in this cohort. Additionally, we conducted candidate gene validation experiments in HepG2 cells. This is the workflow. Measured glucose responses and insulin resistance after 48 hours of olanzapine treatment. We observed 3 genes exhibited higher expression levels and 5 genes showed lower expression levels. This finding provided further confirmation of the association between these candidate genes and metabolic syndromes. Furthermore, we proceeded with the validation of candidate genes in mice. Here are the workflow of validation experiments. We measured fasting blood glucose levels in both wild type and OBOB mice over a span of 0 to 8 weeks. We assessed the area under the curve for glucose and the homeostatic model assessment for insulin resistance in both wild-type and OBAB mice. We conducted Western blot analysis and quantifications for phosphor RS11 and phosphorin northitide 3 kinase in both wild-type and OBAB mice. We also performed H&E cell staining of liver sections in each group of mice after 8 weeks of olanzapine treatment. 3 genes exhibited opposite expression levels between olanzapine-rated C57BL and OBAB mice. These results provide valuable insight into how these candidate genes may play different roles in the context of olanzapine treatment in different mouse models. To further investigate the role of PTPN11, we quantified the expression of PTPN11 in HepG2 cells after treatment with PTPN11 overexpression transfection using qPCR. We analyzed the glucose response level and hepatic lipid accumulations in HepG2 cells. We examined the activities of glucose response in cells that pre-treated with SHP099. Inhibitor of PTPN11. Our findings indicated that the activity of glucose response was significantly increased in cells pre-treated with SHP099. These results suggest a potential role for PTPN11 in regulating glucose response and hepatic lipid accumulation and indicate that pharmacological inhibition of PTPN11 could impact these processes. In conclusion, our study represented the largest multi-omics investigation of match with functional validation of biomarkers initially identified from the schizophrenia cohort. Here are some key findings. We observed imbalanced rare functional variants in the leptin and PPAR gene sets and abnormal methylation levels of ABCG1 in antipsychotics-induced match cohorts. Our results suggest that differential methylation might be driven by genetic variants. And the use of the elegans as a model organism proved to be highly valuable for studying metabolic adverse reactions. And importantly, the PTPN11 inhibitor SHP099 demonstrated its potential to efficiently rescue metabolic disorders associated with the side effects of antipsychotic medications. And finally, we thank collaborators from BIAX institutes, Broad institutes, and the International Serious Adverse Events Consortium, and the Westlake University. That's all. Thank you very much for your attention.